about the difference of the kind of improvement we get because of the reinforcement. So this is just one case where it was compared, but you can also generalize it. So that's the thing sometimes we do, and that has academic value. So suppose if you are interested in writing MATLAB code, you can just write a MATLAB code, and you can also show how different parameters are changing. So here I think the limiting parameter is many times your the stresses because of the bending. So this is because of this case, and for reinforced case, this particular case here, the sigma is same, right? For same sigma, like what is the stiffness in the bearing direction, what is the stiffness in the compliant direction, and what is the load bearing capacity. And what we observe that for this particular case, sigma is same. Sigma y, that is the stiffness in the constraint direction, has increased 3 times, though we lost a little bit, so about 20% increase in stiffness in compliant direction. So ideally it has to be low, right? So it's a low, but still there is an increase of 20%. But what we are gaining is in the load bearing capacity. So here 9 times. And what you can also observe is because here the length of the flexure is L, but in the reinforced section, the length which really means a use or equivalent length for buckling calculation is 1 by 6L and 1 by 6L. So it will be, if you just add them, it will be 1/3. And if it's 1/3, then we will get a square of it, right? So that's why we are getting 9 times more load bearing capacity, because length has, so it's related to L, right? And it's in denominator. So if the length is decreased, the load bearing capacity will increase a square times, ideally, right? So we are gaining here a lot just by reinforcing them, and that's why many times we go for reinforcement. And similar charts you have. So if you have like a solid deflected by delta x, what will happen, how it will affect the stiffness in the constraint direction. So for different kind of p, now you see that is changing for given delta x. So delta x with respect to h, if you draw and then you try to compare the stiffness, it's also varying with respect to P. So higher the P, higher will be the stiffness, which is good, right? And for as it reduces, it will be lower and lower. So I think it's a general plot, and many times it's given in the book and in the literature. Uh, so like longitudinal stiffness, lateral stiffness, bending stress, and buckling load. So these are the parameters we are looking at when you are designing. So general leaf spring, and this is stiffened, so reinforced. This is a wire, and this is also wire. So I think there is a mistake here. And then you can see that how the buckling load has improved in each case. So again, you see 9 times bending stresses, right? So it's the same, but again, I think lateral stiffness, it has increased a little bit, right? And same you see the longitudinal stiffness is it has increased, so it's in constant direction. So if required, that chart will be given to you and you can use it. So I think what we try to understand is the reinforcement helps, and many times it increases the load bearing capacity, the stiffness in the bearing direction without affecting the compliance part. So this is what we are looking for. There are some alternate designs. So for flexure design, or wire flexure, so a single direction constraint. So we use wire flexure many times, but we know that because of the buckling, it's a limited. So very simple design here. What you see here is you just take one strip and then you cut two slots from either side and then you bend. Hmm? So the middle section is like L section, but the two ends are flat strips, uh, horizontal and vertical in the different direction. And now if you try to visualize, so just fix one end and try to see attach one end with any object and try to give xyz translation and rotation. You will be able to see that only along the fold line here, that is the constant direction. All other motions will be possible, and because of these notches, notch here, what you see here is it can easily bend. So you will be able to get different kind of compliance. So just try to visualize yourself, and I would like to fix one base, and the other end I'll ask you to look at it. Another way is you can just take a pin, and what you can do is you can put a sleeve for reinforcement. So either end you can do, and the middle section you can simply fix it, and that will also help. That will be also act as a reinforcement. Very simple example for the wire flexure. So it's a very equivalent to your double universal joints, right? So one end, other end, and you don't have to do much, but you just take a wire and flatten it. So put another one and just hammer it. What you'll get is these notches, right? And that will allow you to. So very simple application, and then you can use it very effectively. So these are some simple examples. So this is out of steel wire. The top one is injection molded part. So that's why I think these days you see a lot of these designs because they are made out of plastics very easily. Other time I also mentioned that the wire, the steel cables or steel wires, very thin wires, but they can be used very effectively as a flexure component because very compliant, but in tension it works really well. Here the caution is it only works in tension. So that's why if you have to use it, you have to make sure that the load coming on the wire is always in tension. And if there is any compressive load, we try to preload it so that it always stays in the tension. And how to constrain them, how to clamp them, that these are yeah, you might be disturbed because there are a lot of noise in the background, so I'm really sorry for that. Yeah, quickly we'll try to mm, So here, for a single dot constraint also, we also use folded leaf springs, and I think we have already discussed about it. So the constraint direction is along the fold line, and this is just one illustration. Suppose if you apply F in plane, it's very stiff, and mainly stiffness is because of the bending and shear, and then we try to uh, use the formulated, try to calculate the stiffness along the this direction. So if there is a force Fz applied along the fold line and Uz is the displacement, so then you talk about the stiffness in the in the constraint direction, and then you get these components. So these two components are mainly, one is because of the bending and the other because of the shear. Mm. And shear you can consider because the it's like a short beam, so then they may come into picture. So you try to use that, and they are more or less in parallel, so you use it. And here A is the area of cross section, T times h, the width, and T is the thickness. A and B are the lengths of the folds, right? And they are used in various application. And one of the thing what I discussed with you earlier is you can design a very good planar stage, you know, which can give you displacement in x, y, and theta rotation, right? X, y directions, translation, and rotation in z direction. So, but only motion in a plane, and it's much better than three wire flexures because there is no shortening effect. So general formulation again, just like a cantilever kind of thing. So if you have a folded leaf spring or folded structure, and if you apply forces at the end and moments, and you have displacement, corresponding displacement ux, uy, and phi, what will be the equation. So this is a generalized formulation. So it's written in terms of compliance matrix. So just inverse of a stiffness matrix here. So this side is your displacement, and the other side you have the forces acting, and connected by either stiffness matrix or compliance matrix. So here, this is the compliance matrix, right? And so this is the generalized one. Now, depending on how you attach them, your boundary condition changes, right? And for different boundary conditions, these are the standard boundary conditions usually you have, and then you can derive it from here. So this kind of questions can be asked in the exam also, like what kind of boundary condition you see. So, and based on that, can you apply? Can you use it, right? So here, like, suppose if it's just moving. So I think one should be able to tell me what are the boundary conditions. If you have this kind of arrangement, what are the boundary conditions here, right? And so uh, here, can you tell me what is the boundary conditions here? What are the what are the boundary conditions you impose here in the first case? Anybody? Can you tell me where you attach the body with the rollers and supported in? So is they are rollers. So what does it mean? What is the boundary condition? Do you put the uh, displacement boundary condition or the force boundary conditions? Anybody? Vishnu, Mohit.
Yes,
So
sir.
just
I
answer.
think
Who is
displace.
answering? Hmm?
So, sir, I think displacement in y direction will be not there.
Yeah. So the uy will be zero, right?
Yes, sir.
Yeah. What about fy?
So non-zero.
Yeah, yeah. So many times I think students make mistakes here. So I think try to look clearly. Huh? The forces maybe if it's not given. So one is applied force, but then you may have reaction moments, and that you have to calculate, right? So okay, uy is zero. What about theta? Phi, in a way. Can you put phi equal to 0 here? There are two rollers. It's not pivoted, right? It's a pivoted, then you can say only uy equal to 0, right? But it can move in x direction, right? Y direction, I agree, it, it doesn't move. But about phi, whether it can rotate. Can you tell me? It's a clamped, right? It's showing clamped. It's not dot there, right? So if it's a roller, and at the end of the flexure, if it's a dot, then you may not have a phi there. But if it's shown like this, it means it's a clamped, right? Only moving in x direction. So your phi is also 0. Do you agree with that? in the first case. So there is no rotation at the end. Same way in this case, rotation is 0. Also, in this case, uy is there. It can move, it can slide up and down, but it cannot move horizontally. So displacement along the x direction is 0, right? Here again, it's inclined. So whatever you write, see here is written ux equal to uy, right? So displacements are related in this case. Hmm? Again, here phi is not changing. Huh? So again, phi, the boundary conditions, you have to clearly check. Hmm? And then equivalently, you should be able to reduce it to this formulation. So just work from here and try to find those relationships. Okay. So what we do, let's just stop here.